Okay, so there is a class of transforms which takes functions and gives you other functions, right? We have seen one such transform, namely the Fourier transform. It came out naturally when we were looking at Fourier series, and then we looked for a continuous generalization of the idea of Fourier series, and we had a Fourier transform, right? So in this lecture we look at another kind of transform which is called the Laplace transform. It is very frequently used by electrical engineers and other kinds of engineers. It finds applications in many physical problems and applied sciences. Uh, in our discussion, we are interested in making use of Laplace transforms to solve ordinary differential equations of a certain kind, and in particular it helps out when you have initial value problems. So that's coming up a little bit later, but in this lecture we will discuss what a Laplace transform is and then look at a few examples. Okay, so let's say that you have some real valued function of a real variable t defined for t. Typically you think of it as time, right? And so it's a signal of some kind which depends on time, and so this is something which starts at time t equal to 0, right? So and so it is in this context that this is useful, right? So and so let us consider s to be some variable which we will take it to be real, right? So it is possible to consider more general versions where you allow s to be complex and so on, but for our purposes let us say that s is a real variable, and so we define the Laplace transform as this function f of s, right, which is another real function of a real variable which is given by this integral, right? So f of s is equal to integral 0 to infinity e to the minus st f of t dt. It looks somewhat like your Fourier transform in the sense that it takes, so there is this exponential factor involved along with f of t, but here we have restricted s to be real, and also the key point is that it goes from 0 to infinity, right? So this gives you another function f of s, right? So you can think of this s as some coefficient. These e to the minus st's are weights that you associate with this function, and you look at every instant of time from 0 all the way up to infinity. In some sense it captures a global aspect of this function, but for every value of this s, so the weights will change, and depending upon how the weights change and the value of f of s will change. So in some sense you're taking all the information contained in f of t and representing in a different way. That's represented in terms of this function which is called f of s, which goes by the name of a Laplace transform, right? So yeah, so it's important to emphasize that this is a meaningful definition of a Laplace transform if this integral exists, right? So we must restrict our values of s such that this integral exists, right? So one can come up with a sort of very sophisticated mathematically intense treatment of the convergence and so on, but for our purposes let's say we deal with physically irrelevant types of functions f of t, right, such that this integral will first of all be well defined. So the only part that we have to take care is that you have s is it lies in an allowed range, right, so that this integral converges. So we will take this function f of t to be functions which I'll just broadly call reasonable functions, right? So we won't get into some technical discussion of what are the mathematical properties that f of t must satisfy so that f of s is defined and so on. So that would be for a mathematically rigorous course, which is not this. Okay, so let's look at a number of simple examples, right? So that's what our philosophy is to define a concept, look at a number of examples and try to apply. Okay, so let's consider this very simple function. So you may have a function like f of t equal to 1. So it's profitable to think of this f of t as a driving function, right? For example, so you have some external force that you're providing to your harmonic oscillator, let's say, and so you can think of a force which is just constant in time, f of t equal to 1, for all t greater than 0, and its Laplace transform is given by just this integral is very easy to do. So 0 to infinity e to the minus st times 1 times dt, which will just turn out to be 1 over s, right? So it is important to check that this integral is a convergent integral. It's a meaningful integral only if s is greater than 0, right? So you want this exponential to decay as t goes to infinity, and when s is greater than 0, indeed f of s is 1 over s. If s is less than 0, then this is not going to converge. So yeah, so we restrict s to be greater than 0 for this very simple example. So let's look at another example. So suppose we consider the function f of t is equal to t, right? So you may put in an external force which goes linearly with time, it keeps on increasing. So now what happens to the Laplace transform of this function? So once again it's an integral, so it's e to the minus st times t times dt. So this is something that can be calculated using integration by parts. So you have u dv, so you put in uv, so t times e to the minus st divided by minus s from 0 to infinity, minus v du, so you have e to the minus st by minus s, and then when you take the derivative of t, you just get a 1. And so at t equal to infinity, this vanishes. At t equal to 0 also, this function, because of the presence of this t, it goes to 0. So the boundary terms go away, and then we are left with just this minus and minus become plus. So you get a 1 over s. Then you have to integrate this once again, but this is an integral which we have already done, right? So you can directly use that. In fact, so this is nothing but the Laplace transform of 1, the function 1, which we already did. So it's 1 over s times 1 over s, which is 1 over s squared. So once again, it is just it's convergent if s is greater than 0. So we must restrict s to be positive. Okay, now we have the next example is slightly more complicated. You may imagine turning on a function which is not just growing with time or linearly, but in fact it's going exponentially with time. So if it is something like e to the at for t greater than 0, it's understood that f of t is 0 for t less than 0, or it doesn't matter anyway. So we are interested in the functional information only for times greater than 0. So f of s here is going to be e to the minus st times e to the at dt. So then we write it as e to the minus s minus a times t dt. So now you can see that basically what has happened is it's like taking a Laplace transform of 1, but now with instead of s you have s minus a. So the answer is just going to be 1 over s minus a, and then now the convergence has shifted, so it's not s greater than 0 but s greater than a, right? So you cannot have a meaningful value for this function f of s unless s is greater than a. So that's the restriction on s in this example. Okay, now let's look at one more example. So suppose we consider a sinusoidal function, right? So it is very common to try to drive your system with a sinusoidal drive, right? We have looked at examples of this kind, and we were looking at inhomogeneous differential equations, and when looking at driven harmonic oscillator problem. So if you have a sinusoidal drive, if you take the Laplace transform of this function, you get, yeah, so a little more work is involved here. So e to the minus st sine of bt. So again we do it by parts. So it's u dv, so you get sine of bt times e to the minus st divided by minus s from 0 to infinity minus integral 0 to infinity. You have to take the derivative of this, so you get b cosine of bt times e to the minus st divided by minus s. So once again the boundary term vanishes at both ends. T equal to infinity, e to the minus st will vanish, and at t equal to 0 sine of bt will go to 0. So basically, so this can be ignored. So then you have a minus and minus becoming plus. So you have plus b by s integral 0 to infinity cosine of bt times e to the minus st. So basically this is the Laplace transform of the cosine function. If we had known this, we could have directly plugged this in, but that is also something that which remains to be evaluated. So therefore we will integrate by parts once again. So you have b by s cosine bt e to the minus st divided by minus s from 0 to infinity minus b by s remains as it is. Then you have an integral 0 to infinity minus b sine of bt times e to the minus st by minus s. So the derivative will give you a minus b, and then you have this minus s coming from this other function. Therefore if you collect all these terms carefully, so now the boundary term does not vanish at both ends. So you have at infinity, of course, it goes to 0, but at 0 you have to be careful and put in b by s squared. So b by s, and then this gives you 1 over s, so it's b by s squared, and then this integral is something that is minus b squared over s squared times the Laplace transform of the sine of bt itself. So in fact we have managed to show that the Laplace transform of this function is equal to b by s squared minus b squared by s squared times the Laplace transform of the same function, right? So basically we can rearrange, and then we have f of s times 1 plus b squared over s squared is equal to b over s squared. So we have f of s itself is just some simple algebra after this, and you get b over s squared plus b squared, right? So this is a convergent integral, as you can check, right? So we have used this during when we were doing this integration by parts. So this is a convergent integral if s is positive. If s for s greater than 0, f of s is just given by b over s squared plus b squared. So let's look at one more example, which is actually a close cousin of this problem, which is if you derive your function, if you have a function f of t which is cosine of bt. So we have seen that sines and cosines are basically the same, some small details are going to be different. So but let's work this out. So its Laplace transform is given by 0 to infinity e to the minus st cosine of bt dt. Now again we start by doing this by parts. So you have cosine bt e to the minus st divided by minus s 0 to infinity minus integral 0 to infinity. If you take the derivative, you get minus b sine of bt, then you have to put in minus e to the minus st divided by minus s. So now this bounded term does not quite vanish at both ends. It's at t equal to infinity it does, but at 0 you have to write it as 1 over s minus b by s. So minus and minus cancels, but there's one more minus sign, so you have minus b by s times the Laplace transform of sine of bt, which we already have worked out. So we can directly get that answer from there instead of doing one more integration by parts. So we'll just write it as 1 over s minus b by s times b by s squared plus b squared, and some simplification from here, and we get s over s squared plus b squared. So we recall that it was essential that s should be greater than 0 for the Laplace transform of sine of bt to be meaningful, and so the same condition also holds for the Laplace transform of cosine of bt to be meaningful. So we see that sine and cosine, the Laplace transforms look very similar to each other. You have 1 over s squared plus b squared in both cases, but one of them has a factor of b and the other one will have a factor of s. So that's all for this lecture. Thank you.